Good evening. We always start at exactly 7. I'm so glad to see so many of you here. And yeah, first of all, my name is Dovydas, and you are in the 3rd meetup of Vilnius School of AI. I have never spoken in such a large room before, so I'd like to thank very much those people who have shared the knowledge and told about this meetup to their friends. Can I get a round of applause for those people? Yeah, you are amazing. Thank you. First, I'd like to talk about what we accomplished during the last month. We haven't spoken for I haven't seen some of you in a month. I have seen some of you in the workshops, but probably we haven't shared a lot of information about how the School of AI is doing. So first of all, we spent this month on really trying to find our voice, what we are all about. And first of all, what I'd like to present is that we have a new format for our meetups. I actually spent a lot of time thinking and soul searching what I want to accomplish with this meetups. And because I had this problem, I want to deliver world-class AI training. That's my goal. I don't want, I'm really not satisfied with mediocre products. And I really wanted this meetup to be the best that you can get. And the problem with that is there are not too many people who can speak about these artificial intelligence topics and who are available. I mean, there are lots of experts. I happen to know some of them, but a lot of them have so busy schedules that they really don't have time or motivation to prepare a full presentation and deliver that for free for you. So my idea was, you know what, that's not the only way. There is another way. And this other way is, there are so many good video talks already delivered, already proven, which you haven't seen. And today, we're gonna experiment with this new format. We're gonna watch a video, and then we're gonna have a discussion about this video. So, you'll see our new format today. On another note, we have 8 squads which are currently doing the workshops. Some of them, actually one of the CE classes is already at the pretty much final stretch of their two So in 2 weeks time, they will be finishing their final project. So who here is from a C class? Yeah, congratulations. Okay, so not that many of you. I have to punish C class somehow. Yeah, so probably they're working on their final projects. That's my guess why they're not here. Yeah, so I'm so happy that people really love these workshops that we're doing, and I'm really very glad that we find this beneficial and they continue to learn artificial intelligence. So with that being said, let's move to the main part of today's meetup, and that's the practical artificial intelligence software 2.0. I'll give you a very short introduction. We're gonna watch a video by this guy, Andrei Karpathy. Who here knows who he is? Really? Nobody? Andrei Karpathy. It's he's one of the top 5 guys in artificial intelligence. Okay, never mind. That's good, I guess. You will be surprised. So what he is, I think he was pretty much a student for a very long time. He graduated up until his PhD. He got one internship at Google, if I'm not mistaken, but pretty much that's how his life goes. He studies, goes to one summer internship at Google, And then pretty much overnight he becomes the director of AI at Tesla. And this is his presentation about how they are applying artificial intelligence in Tesla and how what we are doing, what he's calling software 2.0. This presentation was like so moving for me. I watched it probably like 3 times. So I really want you to watch it too. And you might see the link here on the top. So you have a task. It's not going to be like passive watching, because that's not very valuable. What I'm going to ask you to do is for all of you to open this link. Can you all see that? I can zoom in a little bit. Yeah, so open this link, and what I'm going to ask you to do there is ask questions about this presentation. We're gonna have like a half-an-hour discussion after this video. It's gonna be available, don't worry, like this stays there. Like all out throughout all the video, this stays there, so you can open it anytime. Ask questions about what you feel interesting, or just put some comments. My idea is to have a discussion about this video because I'm so curious what you guys think about it. Okay? And I promise this to be like very valuable for you. So let's start. Mouse is gone.
So I'll tell you about a transformation that I see happening kind of in the area of software engineering. Now, to tell you that story and to tell you about the trend and the transformation, I actually have to begin this talk 1 million years ago. So 1 million years ago, this is us, the human sapien species. We're mostly throwing rocks at each other and hunting for food. So things are going along pretty nicely. And then at some point, we're a pretty clever species, so we start to master fire, and then we start to adopt agriculture, and then we start to build some machines. I promise this has a point, by the way. And then we start to build more complex machines, so especially computers, first mechanical and then electrical. And then here we are, a few tens of thousands of years later, and we're writing software. And it's actually like pretty incredible how far we're able to get with the, in terms of like engineering and using technology and building tools. So in particular, we have this engineering approach where we kind of iterate over a lot of problem areas. The following algorithm: we identify some kind of a problem that we'd like to solve, and we are a resourceful species, so we break down the problem into smaller problems. We design algorithms for each individual problem, and then we compose them to solutions and systems, and we build stacks on top of stacks. So for example, the TCP/IP stack is super interesting, impressive. The Android software stack, the AWS stack, these are all like large systems of software, and we're able to get them to work incredibly well, and get really surprisingly far with this approach of breaking down problems, addressing all the pieces one by one, and then plugging them all together into complex systems. And this kind of like started to break down a little bit recently, where we came across some problems where this doesn't seem to be working extremely well. So I think image recognition is a very good example where this kind of problem starts to break down a little bit, because we at some point decided that it's kind of useful to actually detect what's inside images. So say we want to say that that's a cat, and now the question is, okay, how do you build a recognition stack? Because that image is 1 million numbers, and I'd like to go from 1 million numbers to here's a cat or a boat or something like that. So how do we build a recognition stack? So of course we kind of put on our engineering hats, and I think the first approaches to computer vision were along the lines of that we're familiar with. So okay, there we go. So visual recognition in the early days was kind of putting on the engineering hat and trying to figure out, okay, how does perception work? Well, we have the brain, it's doing some stuff, let's try to figure out how the brain works, let's break down all the pieces of the brain or try to come up with it kind of in terms of engineering, how should we break down the problem? So we take the input image and maybe we start detecting the edges, and then we, there were lots of theories about how perception worked, and we're going to break down the problem and, first maybe detect small earpieces, etc. And so there's actually a really good book, for example, from David Marr, where he proposes this recognition stack and lays it out, but never actually got around to implementing it. And it's an extremely complex thing to implement because, as you may be aware, some of these problems are actually extremely difficult. So if you try to engineer your way through it, you will arrive at a huge amount of complexity because these million numbers can, the subset of these million numbers that corresponds to a cat is extremely gnarly, and it's really hard to actually build the tooling for doing this recognition task. Okay, so then we took a little bit of a step back, and we did not aspire to actually develop the entire recognition stack. We're just going to develop a few features that measure some statistical patterns in the image. And then we had a tiny bit of machine learning on the top of these features. We have a small linear classifier at the end, and now every image is represented in these features that we engineer and that we design, but we train the classifiers based on some data. And then this kind of went a little bit crazy. So there's a paper from 2011. This is when I got into computer vision and I started my PhD. And this got out of hand very quickly because there were so many different feature types. So this is just from a paper in computer vision, and it was kind of crazy. And so these are all different feature types. And I had this code repository where some of the features are in MATLAB, some of them in Python, some of them in C++. You have to compile it. You create these feature vectors for each image that are like 200,000 dimensional. And then you put SVMs on it. It was a complete disaster. I think people who are getting into the area of computer vision today actually do not appreciate how terrible it was before, now that they just train ComNets. So we took a step back and we're like, okay, maybe we should not be designing these features. Maybe we should not be trying to engineer the system. We're stipulating much less of the architecture. We're just going to kind of lay out the rough layout of the architecture, the way the convolutional layers kind of plug together, and then we're going to learn much more of the system. So now we actually train through the full system, but we're still specifying the architecture. So we took a step back and things worked really well. And some of the latest state-of-the-art kind of results in image recognition actually go beyond that. We're not even designing or architecting the architecture itself. We're actually stepping back and we're trying to optimize over the architecture. So we don't even trust ourselves to actually establish the architecture. We don't know what that should be. So we just search for architectures that seem to work well on our data sets. And this is working quite well again. So the trend really here in the example of image recognition is that as the complexity of the task increases, the approaches that you see, the state-of-the-art approaches that you see, take on a different form. So in the beginning, when you don't have a lot of data available to you, you're doing most of the work yourself. You're hard coding and engineering. But as you have more and more data, you are able to afford solutions that require less and less engineering from you, and you offload that engineering to the optimization. So the approach in what I refer to as software 1.0 is kind of like all the code that you're familiar with. This is the engineering design approach to solving problems. Say we try to come up with a stack, and this requires a lot of domain expertise, and we're going to decompose the problem, design algorithms, plug them together, and then we can of course evaluate whether or not some solution is working. For example, in the case of image recognition, we can evaluate the accuracy on the test set. So you can engineer that pipeline yourself, or you can kind of realize that this evaluation is fairly straightforward. I can take a number of images and I can run them through my system and I see how well it performs. So the evaluation is fairly cheap and you can do it. So how about we step back, engineer less, and try to look for programs that actually work well according to the evaluation criteria. So we're seeing this across a number of areas, and just one more kind of like mental model that I find interesting or useful to think about this is the following. Effectively what we have is we're trying to identify a point in program space, and this program that we're trying to find is we'd like it to basically, we like to have the property that when you run it on test images, it classifies them correctly. And when you're trying to put on your engineering hat, and you design the pipeline, you're really identifying a single point in that space. Okay? And you can't write very complex programs, so you're kind of like around the origin of this circle. And we can do that and we can design it. So really the new approach of this new stack is that instead of identifying a single point, we're actually carving out a region of the program space. Like for example, when you identify an architecture, you're saying that, okay, the program should look something like this, but the details, the weights, are to be determined by optimization. So we really carve out a set of programs that we think may work. And then we're paying the price in compute to actually find the program that works well within that set. And you can do that if you have access to huge data sets, a lot of compute, and we can just find things that work well. And so this is kind of like, I had a tweet, this is a few months ago. The tweet said, gradient descent can write code better than you, I'm sorry. And a lot of people are like, what are you talking about? This is what I was talking about, is that really the optimization, gradient descent in the case of neural networks, is searching for a program that satisfies simultaneously the labels for all the images in its training data set. And so this has been an ongoing transition, not just in computer vision, of course, but in a lot of other related areas, in areas where evaluation is fairly cheap, but where we don't actually know how to write that program. We don't know how to design the system. So this is the case in speech recognition, machine translation, and a lot of other areas. Recently, Google is probably at the forefront of turning itself from a giant engineered system into a giant kind of a learned system. So there's this one paper that I kind of like. It's one model to learn them all. It's a single giant neural network that's trying to simultaneously do lots of different tasks. And so maybe, currently Google is written in mostly 1.0 code, and it's a giant repository of C++. Maybe in the future, Google is just a single stack of a giant neural net or something like that. That would be kind of cool. This does not only apply to images. It really applies to any area where, again, you can evaluate whether or not something is working. So, for example, in the case of reinforcement learning, we don't actually have a data set, or in the case of, say, playing chess or Go, we don't actually have a training data set, kind of, but we can generate rollouts of a game, and then we can measure whether or not a program is playing well because we put it against other programs. So we have an evaluation, so now we're set. We just kind of identify a program of the space that seems promising, and we pay in compute to find programs that work really, really well. And if you actually throw enough compute at it, you can actually find programs, especially AlphaGo and AlphaGo 0, that work much better than engineered programs. So state-of-the-art and engineered software for chess would be Stockfish, the chess engine, and we're doing really well there. And the other point I'd like to make is that this is not even specific to neural networks. This is a wider trend. So there's a PhD thesis from a student who was at Stanford that I really like. It's called Stochastic Program Optimization for x86, 64 binaries. The idea is that we can take assembly code, and if you can measure, the speed and the precision or the accuracy of some kind of a small piece of program, then you can basically come up with some mutator functions on top of different assembly instructions, and you can kind of pay in compute to search for programs that work really well, and that actually works quite well. So in this case, it doesn't even involve neural networks. It's just searching for in a space of assembly instructions. So we're seeing this, and robotics is another kind of area where this transition is kind of dear to my heart. Is in robotics, you of course have a lot of these engineered systems. So if you want to, for example, get a robot to move something from one place to another, then you can imagine, writing a program that understands the perfect 3D mesh of what's there. You can try to figure out, control planning and so on. And now we're seeing the first iterations of doing pixels to torques, where we're trying to just make a neural network write that code, and that's kind of ongoing. The big asterisk in this area, and just to comment on this transition, it's not complete across all the areas. So, for example, in the space of robotics, Boston Dynamics, that has probably the most impressive robots, is still entirely software 1.0 based. There was a person who spoke at NIPS 2 years ago or something like that, and was pointing out that this is not even machine learning, it's not even deep learning, it's all engineered, so that's working pretty well. And the other caveat in this transition, a lot of pushback that I've received, is people, it's a little bit of the reason I call it software 2.0 is that I'm just trying to differentiate it from software 1.0 kind of that we've been writing for a long time. So I'm not trying to make the point that 2.0 is going to replace 1.0, but I think that will be the case in many areas, but probably, certainly not all of them. So in that case, 1.0, 2.0, it's kind of on the side, not better in strictly some ways. So for example, to compile 2.0 code, really, you need a huge amount of 1.0 infrastructure. Data sourcing, cleaning, we're going to go into that, the base operating system, distributed training, evaluation, visualization, all these kinds of 1.0 tools that we know how to engineer, and then we're using them to compile 2.0 code, which is something like a neural network. And then we deploy that neural network somewhere, and we don't need all the surrounding infrastructure, we just need a few more matrix multiply libraries or something like that. So really, it's a new type of software. It's not written by humans. It's written by optimization, and it's written in the language of weights. In the case of neural networks, and those weights can't be written by a human, but we know how to evaluate something, so we can find weights that work well. It's really just fairly straightforward. There are a huge amount of benefits to software 2.0 that I'd like to briefly go into. So the first thing is about the stack is that these programs written in 2.0 can be very computationally homogeneous. This is highly convenient in many cases. So for example, a ResNet, state-of-the-art convolutional neural network, is extremely homogeneous. You're basically doing convolutions, rectifiers, and pooling. And pooling is on its way out. So it's really just convolution and thresholding. It's really just the full stack. Like normal, you can think of like a 1.0 code base in C++ would be like a pretty sprawling, gross thing. Because it is so computationally homogeneous, it's also very hardware friendly. You can bake it into hardware quite easily. A lot of other nice properties are that it has a constant running time and memory use. So if you compare a sprawling C++ code base that could be doing recognition to a neural network forward pass, then the C++ code base will run at different amounts of time, at different time steps, depending on different images. It can have infinite loops and things like that. A neural network will never do that. And that's a really nice property to have in cases, for example, like in a self-driving car, and in a complex stack that needs to work in real time. We can actually make, this forward pass of this network always takes exactly the same amount of time and memory. There's never infinite loops. You don't swap to disk or anything like that. It doesn't happen. The stack is also extremely agile. This is a kind of unappreciated property, I would say. So for example, if you need to create a program that has the same functionality but runs exactly twice as fast, potentially compromising some of the accuracy, then this is trivial to do in software 2.0, but it's like highly non-trivial to do in software 1.0. So in 2.0, I'm just going to remove some of the channels, exactly half the channels, and I retrain my network, and there you go. You have something that works slightly worse and runs exactly twice as fast. So this is really hard if you were to do this in C++ code base. You'd have to put up your profiler, debugger, try to figure out kind of where all your time is spent, and iterate, and that would be pretty gross. And the other very nice property of this stack is that you can fine-tune, also really useful. So you can basically think of a 1.0 code base. You have all these function calls that are nested in your software stack, and now you have some kind of evaluation criterion at the top of it. You can't automatically tune all the layers below you. It's kind of like you're using a library, and that's a fixed thing, and you are operating with their library, but you're not going to push code or change code to the library that you're using, like OpenCV or something like that. But this is something that's kind of like the first few layers are the OpenCV, and the last layers are doing something higher level, and you're fine-tuning through the whole architecture. It's actually kind of magical, and that works, and that can be done. And finally, last but not least, it works extremely well. So just in terms of numbers, which is really nice in many cases. So I currently work at Tesla. I joined maybe 11 months ago, and I work on the autonomous driving team. So really, Tesla has the largest deployment of robots in the world. We have about 250,000 vehicles out there, and our task is really just to make them autonomous and drive by themselves. And just to tell you a little bit of some stories from the trenches of how this transition is playing out kind of in Tesla, and I think that's a good example, but I think this transition is of course much wider and happening across many other companies. So when I got there, really when you look at the stack of the self-driving car, it's actually fairly straightforward. We have a stream of sensors that are coming in at the bottom, and really what comes out of the stack is really just the steering and acceleration, two scalars. And when I got there, there's a bit of pre-processing, then there's some kind of a neural network that's doing a lot of the base recognition, just as is the case in many other, probably everyone else. So there's a convolutional network, and there's a number of amount of post-processing that is all written in 1.0 code. And kind of since I joined, we've been doing a little bit of this. The neural network is kind of taking over the stack, gobbling things up, and also working quite nicely in the process. Just to give you an example of that transition, actually, by the way, if you're a deep learning person, you can't look at that diagram and just think to yourself, you're seeing this thing grow, and you're just thinking oh man, just obviously that should all turn blue at some point. But yeah, we have to wait for that a little bit, I think. So just an example of this transition and what this looks like. So we have to, for example, detect if a car is parked or not. It's a useful feature to know about a car in the world because we can control differently around the car. So one approach you can imagine is that there's a neural network that does the detection, and we get some bounding boxes out of the neural network, and then we have a number of post-processing stages to try to determine if some number of cars are parked. So maybe we can create some kind of C++ rules around, okay, a car is parked if it hasn't moved in some time, and it's on the side of the road, and maybe there's a pattern of cars, then that's probably parked. So you can come up with these brittle rules in software 1.0 stack and try to design it. But again, the trend is you should not be designing, you should be stepping back. And in this case, maybe a better way to do that is a car is parked if a neural network says so. And now my task is really just to collect a huge data set of parked cars and not parked cars, which by the way is much easier. And then I'll have the neural network write the code. And that actually works quite well. So this has been kind of ongoing throughout the stack, and it's working quite nicely. Now, a few more kind of points around kind of stories from the trenches of programming the 2.0 stack, something that's going on at Tesla, something that we're trying to get to work quite well. I think one of the kind of major philosophical conundrums is kind of like, okay, if optimization is doing most of the coding, then what are the humans doing? What is our goal? What are we supposed to do then if it's all automatic in that part? So we're kind of used to in computer science, designing cool, clever algorithms, measuring their running times, and doing things that look like that. But what does it look like when you program in the 2.0 stack? Well, what I've seen is that the workforce in your programming team actually splits in two large groups. The first group actually does a huge amount of labeling. Okay, so we have a huge amount of people who just look at data, and we create pretty complicated interfaces for them to label and annotate data. And this is telling the program really what the constraints are. What are you supposed to satisfy? How are you supposed to work? So those guys are doing most of the programming actually, and we develop some of the surrounding infrastructure. So the data labelers are the programmers, and they program by telling the optimization how to work, and we help them out. So we have a lot of tooling for, okay, these people need to be very efficient. How do we make them very efficient? How do we flag disagreements? These are pretty complex tasks in many cases. How do we identify interesting data? It's not just about the scale of your data set, it's about its variety. This is extremely important in getting these problems to work. And you have to, of course, clean your existing data set, and you have to visualize things and so on. I'm going to dive into slightly more details about what that surrounding infrastructure looks like. But we spend a lot of time developing that stuff for the labelers instead of developing the stuff on the left. So really, since I joined, it's kind of interesting, but the amount of sleep I lose over things has shifted. So I come from a PhD background. So as a PhD student, I'm working with ImageNet, and I'm trying to come up with a cool algorithm, cool network, or something like that. So I spent all my day trying to figure out, okay, what does a cool architecture look like? And so my data set is given, and I just do some of the work, and I get some numbers, and I put them in tables, and I go to conferences, and it's great. So at Tesla, yeah, it's just shifted a lot. So in particular, for image recognition, there's a huge amount of correct answers in some ways, and training networks and so on has become kind of pretty straightforward. You import TensorFlow STF or import PyTorch, and you just run it. You train it on the data set. But massaging the data set, cleaning it, assembling it is just like a complete disaster because there's a lot of things we want to predict, and we need to collect data set for all of it and to make sure it's large, varied, clean, and that takes a lot of time. So some fun lessons learned the hard way. The first thing I learned is this piece of data labeling is extremely highly non-trivial. So you'd think this would be straightforward. It's super not straightforward, and that's why it requires so much infrastructure. So for example, we have an image we're trying to drive. So of course what's really important is, well, we need to be able to identify the lane lines so that we can stay inside them. It seems kind of like an important thing. Okay, so, well, there's a lane line there, lane line there. How hard could that be? You go out to the real world, it can be really, really hard. So you come up across images like this. This is in Europe, and then you're suddenly not sure. So you create your labeling instructions, and then you label some data, and then you come up with this, and you're like, oh man, I don't know, should we be zigzagging? Should we be interpolating? It's not really clear how you should be labeling this. Do we deal with this in network, or do we deal with this in post-processing? So philosophical conundrums. Then you come across here, and you're like, oh man, I'm not sure. I guess we ignore that. I guess. And now you have to add this image to your labeling documentation because people will be confused. And suddenly your labeling documentation becomes like, a billion pages. You come across this, and like, what the hell is that? Like, why? Do you go around? I don't know. So this is in our labeling documentation. If you're trying to annotate vehicles on the road, you might think it's straightforward. You put bounding boxes around cars, right? We should probably, do that. And then you come across things like this, pretty common. Is this 4 cars? Is this 1 car? Is it 2 cars because of a joint? I don't know. I'm not sure. But you have to come up with something, standardize it, and make it work. You think traffic lights are fairly straightforward, right? So you have red, orange, green. Is it 1 of the 3? This gets like really crazy really fast. So, so I don't even know how to come up with a schema for how to represent traffic lights in the real world, to be honest. Even the labeling documentation just balloons up to quite a few pages, and I didn't even know that blue traffic light was a thing, so it's not in documentation. And then we came across that, and I was like, oh man, I think we need to add a blue traffic light. And now what's going to happen, right, is you're going to, since blue traffic light is so rare, you're going to have 1 billion examples of your green traffic light, and you're going to have like 10 of them sprinkled as blue ones in your data set. And that's probably not going to work, right? So now you have a problem. Speed limits, also highly non-trivial. You think it's just a number, it's not a number. This gets AI complete extremely fast. So a speed limit can be 40. If you're a truck, after 6 p.m. on a Sunday during the blue moon, like I don't know how to label this. And I hope the one on the right is a joke, but I'm not even sure anymore. So really, like the reason I lose sleep over this is because teaching these data imbalances, again, it's not just about the size of the data set. If we get data at random from the fleet, we're going to get a huge amount of driving forward on a highway. We can't just afford to do that because at some point the neural network gets it. We have to be actually kind of like careful. So for example, in the case of vehicles, we actually want to know their class because these vehicles move differently in the real world. So cars will move in a certain way, and trolleys will move in a certain way. We want to model that downstream, so we actually need to worry about their classes. But suddenly trolleys are so much more rare than cars, so it's a problem. Traffic speed limits also have a wide distribution. So you have a lot of speed limits kind of cluster around 45 miles an hour range, and then you have very few speed limits outside. And now you need to worry about this because your network will not work extremely well when you don't have too many examples of it. We see this example, for example, with blinkers. We'd like to identify blinkers because that hints that people might cut into your lane. So collecting, for example, data set of is the blinker on or not is highly non-trivial because, again, you need to be picky in your data set because if you just collect it at random, then the blinker is always off and it's not going to work. Orange traffic lights also appear just for brief moments, so it's really tricky to catch it. In terms of the label distribution, these are very uneven distributions, and academia does not pay enough attention to how we actually deal with these uneven distributions and how we train networks in those cases. It is also true of the data distribution itself. Most of our images look potentially like this if you're not careful, and we work there. And then when you get to areas that look funny or new in certain ways, like here, then will of course not work extremely well. Or if you go to San Francisco and the world is sloping upwards, it looks funny, and the network might struggle in those cases. The other kind of interesting thing that I discovered is that labeling is not just, you can't just get a data set. It's not a thing. You have to grow a data set, and it takes time and attention, and it's painful. So for example, Tesla famously tries to save money all over the place. So instead of having a dedicated sensor for sensing whether or not it's raining, Elon looked at this and he's like, well, you see raindrops, so vision can do it. And now it's my problem. So we have to look at whether or not it's raining and if there are raindrops. Okay, so you collect data, you train a model, you try to deploy it, it will not work. It will not work because there are lots of cases where, in this case, it's straightforward, but then you have a whole range of, this is sometimes working. I have non-deterministic liquor. So we have ice on the windshield, we have smudges. The first iterations of our auto wiper feature, like really liked tunnels. It would get super excited, it would be like, whoa, and it just like starts wiping like mad. So we're like, holy crap, okay, suddenly we need lots of tunnels that are labeled as negative. This is how you program the 2.0 stack, okay? It's like, oh man, like, okay, I needed to not turn on in tunnels. Now I need lots of tunnels labeled as negative. And it was really excited about sun as well. Because the problem is the sun, the way it illuminates the windshield, it brought up all these smudges and it made them look like raindrops. And it was super non-trivial to actually tell apart those smudges from the raindrops. And this ended up being pretty difficult. So, our data set at the end of the day is like super crazy. I thought this was straightforward. It's not straightforward. It mostly works now. We've shipped it recently and mostly works. But we're still iterating on it. Some people have a lot of fun with this. There's a video on YouTube. Will it wipe? So it turns out that our auto wiper will wipe on cornflakes, things those are raining. And they've examined lots of different things, so cornflakes will wipe, but ketchup or whatever that is will not wipe. That's not so that was hilarious. Okay, all right. So really, like my overall lesson from trying to get all this stuff to work in practice is that this tool chain for programming the 2.0 stack, there's a huge amount of benefits to it. It works really well, but it's super non-trivial and involves a huge amount of infrastructure that is legitimately new and has not been around for a while. And few people really realize that this infrastructure that needs to be written is a thing. It's not just about, you can't just collect your static data set. There's a whole huge amount of work to do and lots of low-hanging fruit. So for example, in programming software 1.0 stacks, we're actually very good at that. The reason we're good at that is that we have a huge amount of kind of help from the computer. So we've developed a lot of tooling for helping us program. So for example, we have IDEs that have a debugger, a profiler, go to definition, syntax highlighting, lots of tools where the computer is trying to help you write code. So what is the equivalent of the IDE for a software 2.0 stack? That's a question for all of you to some extent. We have some ideas at Tesla, and we're building up the software 2.0 IDEs. I'm still kind of trying to figure out what they look like, what the pieces of it are, what modules of it are. So it's still an ongoing process. We have some guesses, but I'm not brave enough to actually show you concrete examples. But really what it comes down to is we don't write the code anymore, the labelers write the code. We have to, and the code is implied by the optimization based on your data set. So accumulating a nice, varied, large, clean data set for all the different tasks you want to do, and worrying about all the edge cases, and massaging it is really where most of the action is. The coding is now done by the optimization, and that optimization is actually fairly straightforward to do. And of course, we still do a lot of training of convolutional networks and so on, and I'm familiar with that, and we do a lot of that at Tesla, but this is where most of the action and most of my sleep is really lost. But yeah, if we can get this to work, I think that would be pretty exciting. In particular, we'd be able to get these robots to drive autonomously, and I think Software 2.0 Stack will be really instrumental in getting that to work. And if this can drive autonomously, then we will sell more of them. And if we sell more of them, then the future is going to be good. And really, the sky's the limit. So if you're a hardworking person who really wants to push the 2.0 stack to its limit, then I encourage you to reach out. Yeah, I hope that we can get this to work, and it'll be really cool. Okay. Yeah, thank you.
Hey, so you're hopefully not asleep. Do I have any questions? Let me check. First of all, how do you feel about the video? Can I get a raise of hands who loved it? Wow, quite a lot. Now, who really hated that? I mean, be brave. There's no judgment here. You are allowed to express your opinion. Okay, nobody hated that. That's strange, because actually what happened in the real world, there was a lot of media and blog posts claiming that, oh no, he's wrong. He's wrong about all of that. How dares he call this thing software 2.0? It's stupid. I mean, it's just labeling the images. How you can call it? You cannot even call that programming. That's something that's just annotating images. And you can read about all the various arguments. For me, I kind of feel first of all, this is the first time I watched this video after dealing with kind of similar situation at my current workplace. I have to deal with data sets a lot more than I was just studying deep learning. I mostly dealt with what's the best architecture, what's the best let's do some benchmarking. Is exception a better architecture than Inception v4? Or how ResNext 101 is doing? Is it any better than those two? So now I also deal a lot more with the data. So I'll give you a few minutes to write the questions. I see a lot of questions are popping up now. So first of all, I would like to ask for the first question. Do you think that what he's talking about, labeling the images, do you think that that can be called programming? Sure, go.
Well, because if you want to make it automatic, you have to do some programming.
You said yes or no?
Yes.
Yes. So she says that it's yes, because you have to do that to make those machines work, do the rest of the job. Right? Good.
I think it's not programming.
Right,
There's
and why?
no mental work involved in labeling images.
Mm-hmm. Okay, that makes sense. He says it's not programming because there's not a lot of like mental work involved in just labeling the data. What other opinions do we have here?
The question is if he, as a human being, already has a mixed up feelings about some of the data. He doesn't know how to label at all. So can we say that it's quite a mental work, quite a mental
It's
work?
different thing from programming.
What is programming then? Define them.
Writing instructions to computer.
Oh no, I
Yes.
don't agree with that.
It is.
Yeah, because programming was invented way before computers were invented.
Okay, it's not. It doesn't have to be a computer. It's writing instructions to a machine. It
Not
doesn't have to
necessarily.
be a computer.
We
All right, I'm gonna like ask you to stop. You can fight. You can fight
We're
afterwards.
discussing.
I actually love both of these arguments. I want to like, because it's really hard for the people in the back to hear you, and I only have like this one microphone, so I'm just gonna be the summarizing voice. So what he's saying that because it's so difficult, because even like Andrei doesn't know how to label some of the data, it is still like mental work. It's still teaching the computer. I actually read this very cool article by Microsoft, and they expect that computer teaching is gonna be the new programming. I mean, the old programming is not gonna be replaced because it's so huge right now. We have such a big shortage of developers, but they also expect that the new generation of programmers will be showing computers, not necessarily in this way, but like in many different ways, how to do something. Like you don't, because look, like you have your ID, you have so much help from the computer, and Andrei kind of tries to show that you have so much help from the computer that you just have to like write this algorithm or find it on Stack Overflow and then basically put it to solve this problem. I mean, then I was mostly working as a developer. I kind of knew the best practices and I was applying the best practices, but that was the easy part. The hard part was make it work in our system and make it work on edge cases. And that's exactly the hard part which we have in Software 2.0. So for me, just because of that, it's programming. Right, so next question. Will it be possible to watch or download the video later? Yes. Short presentation of what School of AI is. Sure, that comes right after the discussion. We have robots that programmed with so-called Software 2.0. Could I post a link? Sure, you can do that on like our Facebook, on our Facebook group. If you want to share anything with us, that's the best place to do that. Software 2.0, isn't it another name for end-to-end machine learning? That's a good one. So what do you guys think? Let's start with an easier one. Who knows exactly what machine learning is? Who knows approximately what machine learning is? Very good. So I'll ask like some new people, because those who spoke, they're braver now, because nothing bad happened. That's reinforcement learning. You speak up, nothing bad happens, you feel good. I'll do that again. So those people always raise their hands. So somebody new. I saw some hand there. Can you like re-raise that? Yeah, you can from the back.
machine learning, actually he explained was quite good that we don't set up programming system, we don't set up exact code, we just set up organisms which use, depending on what kind of machine learning system it highly depends, and obviously it's best to look for either a GitHub or Stack Overflow to best algorithms, but in short, set up algorithms, for example, analyzing pixels of some image. You just analyze them, set up code, and that's it. It uses the fact that machine learning can implement, evaluate itself very, very fast, and that's it. Is it another name to end? Is it another name end-to-end machine learning? It doesn't matter. I mean, I can understand, as you mentioned, that a lot of news outlets say like outraged by this claim that software 2.0, but it doesn't matter how we call it. We see that it's used in Facebook, we see that it's used a lot of in Google. Obviously Tesla can be a good example. So we see that it works. So what matters?
He actually has a very good point. I really love your ideas. I cannot really summarize all what he said right now, but like the most important, I guess, idea is that it doesn't matter how we call it, it just works. That's the important thing. So I'd like to explain a little bit better what machine learning is. So in usual programming, you actually get some data, get some code, and you get the results. In machine learning, you get the data and you get the results, and machine learning makes the code. So that's the difference. You start with the results, you start with the data, and then you get the code. In usual programming, it's code plus data equals results. Any more? Who wants to talk about this one? Okay, we have a new question. This 2.0 maybe it's not so important for other applications than cars. Okay, yeah, that's a very, I guess, interesting opinion. So who wants to challenge that? Yeah, same guy?
Yes, it's very important everywhere. Like the easiest example that everyone can get is economics. I've seen that some machine learning algorithms you can use as data set economics, like how some company perform or how economics perform, and this can be used to calculate, or not to calculate it, to predict it in the future. And that's one very small example. You can use it in number of fields, especially in computer science.
What he's saying is that you can use that in economics, definitely that's true, and you can use that basically everywhere. You can use computer science. Remember in the video he's shown us that this gradient descent can actually write assembly code and even make it much more efficient. So he like in the beginning he's shown us two like programs of assembly code, and one of them was written by the machine, the other one was written by human, and the machine one was like much shorter. So I believe, like I very strongly believe that it can basically be used almost everywhere usual coding systems are used. You can optimize the code itself. So why, like, it's pretty easy to like see the argument that you can reuse that for basically any piece of code. Right? Let me see. We have. Do anybody wants to challenge this one? Okay, let's move to the next one. What are other applications of 2.0 which wouldn't include image recognition? Who has an answer for that?
Voice recognition.
Yes, voice recognition, excellent.
I've also heard a lot about diagnosing diseases
like getting all the data about the person and diagnosing a disease before it happens something.
Yeah, so what he's saying is that you can use various inputs, like probably test results, or...
Test results or just sensors on the human body and everything.
Oh yeah, sure, sensors on your like smartwatch, and you can identify if you have any disease. And I mean, it doesn't have to involve any like images at all.
But mostly we are talking now about problems which are, you do some statistics, you get out some prediction, that's it.
That's what machine learning is.
But
Like pretty much a branch of statistics combined with programming.
anything else out of that particular set of problems?
But these are like huge problems. Anything can be statistics. Images can be like converted to numbers, can be converted to like machine learning, deep learning models. Gameplay. You guys, probably most of you know about AlphaGo Zero or like AlphaGo Just. So that's like one example, gameplay. Probably some of you know about OpenAI 5. Can I get like a raise of hands again? Who knows OpenAI 5? Not a lot of you. That's an amazing like achievement that this huge artificial intelligence, like reinforcement learning agent, managed to beat semi-professional Dota players in 5-on-5 competition. And Dota, I'm not like big on computer gaming, so I might be wrong, but I think it's like something like League of Legends. Am I right? Very good. I was so scared to say that because I am not sure about it. Yes, so that's League of Legends. And if you ever played the game or you have seen the game, you know how complex it is. You can basically do a lot of actions. The agent has to like really strategize, and at this point, basically, it's just one step from like putting this thing into like a robot body and letting it loose on like the real world. Because ultimately there is no difference. You just walk there, do some action, get the reward, do whatever the reward signal tells you to do. And in a way, I understand that humans work in kind of similar way. We just do what our reward signal tells us to do.
Well, except physics is a bit different. So, I mean, in games it's pretty simplified, I would say.
Yeah, but I completely agree with what you're saying, but physics is like the easiest thing.
No.
I mean, no, for the agent. I mean, you just have to obey it. You don't change physics, like the rules,
Yeah,
the
but if you're
laws of
talking
physics.
about putting it into robots,
Yeah, that's. I mean, robots develop on a different track. Once we have like good robots, it's about the motivation, what the robots do. I'm not saying like in any way that the physics of the game can even hold a candle to the real world physics, because those are like infinite, we don't understand them, and the physics on the game, they are like developed by some like programmers, but in a way like the agent just obeys the laws of physics. So in my opinion, I might be wrong, but in my opinion, that doesn't really change the like behavior of the agent. If the agent sees that it's valuable to like drive a car and like pick up Uber passengers, so and like make money this way, then for me it's like kind of indicates that the agent is smart, or I guess like a human is smart. Or do you want to challenge that?
I mean, you said it's one step. I think that's pretty big, and if we are talking about data, I mean, you can't have data on every single happening or accident that could possibly happen. So when you're modeling, I mean, you of course have to think about some laws of physics as well, how it, for example, affects the movement of a car, for example. So, I mean,
I
many
see.
things need to be considered. That step is not so tiny.
I understand. Now I got what you're saying. What she's saying is that the real world is infinitely more complex than the very sandboxed
Yeah.
game environment.
But-
And these edge cases, they make the real difference.
Yeah.
Right, yeah, very good point. Actually, I haven't thought about it now.
Yeah, because the games are what we put in them is what we have basically.
Mhm.
And in the real world, I mean, it's more complex, I would say.
Great idea. Actually, I really love these discussions because you learn a lot. You haven't, I honestly haven't thought about it, but then she said that it suddenly makes sense to me.
But in real world scenarios, most of these complexities doesn't matter because for practical reasons, you have quite limited set of rules even for human beings. And if something unexpected happens, we as machines, we are not perfect either. So we are failing the same way as artificial intelligence will fail.
So we better have artificial intelligence better drivers than humans have.
We will have.
We already have.
We already have. But
So if you would compare
we should-
how much deaths you have right now when a human's driving and the length or quantity of kilometers what these autonomous cars did, so it's quite obvious that already now the technology is much better than humans.
We're worried about artificial intelligence extremes much more than we're worried about extremes in human behavior. Somehow. That's a real problem.
Thank you very much. I see this gentleman in the back has something to say.
We also teaching human behaviors to robots by step, because they should support us. That's why they should learn human behaviors. That's why robotic engineers trying to absorb, they trying to reflect human behaviors to these robots. Or another say, for instance, the sporter robots always got different kind of movement styles. Like when we try to catch them, they always try to be with human at the beginning. But maybe at the future, they will be more echo with movements, echo with human beings. Like they absorbing human behaviors. With that, they also be learning everything else about humans. Deep learning progression. It's not about image recognition. It's about recognition. Everything's about the world and human and anything else.
What he's saying is those agents kinda are the current agents are just the first step, and in the future they might be much more efficient. Well, not efficient, just better. Because honestly, look at it, it's just the beginning. These are the first steps. We are so judgmental about the future by just seeing the first step. I mean, imagine seeing a computer in 1965 and determining oh, these are not going to be any good in the future. So that's the same thing we are judging these artificial intelligence agents, which, I mean, deep learning is 5 years old. I mean, it's very old, but kinda in a way it's 4 or 5 years old, because it's just having caught momentum. It just got the hardware pretty much 5 years ago. And now we have this explosion in all directions. I mean, reinforcement learning, supervised learning. Reinforcement learning, by the way, for those of you who don't know, is when the agent learns to change its behavior from experience. It shows one action, this action got a negative reward, it shows a different action. Sometimes it takes 10 actions, then it gets the reward, then it tries to track which action was this reward attributed to. So it's like extremely interesting subject. I would very much recommend for you to read about reinforcement learning. I'll try to post something about it on Facebook. And I think we are kind of out of time for the discussion. So I hope that was interesting for you, that was as interesting for you as it was for me. And now it's time to have like a 5-minute break. Let me, before that, so yeah, discussion. Now we'll have, now we'll talk about the workshops, and I'm gonna give you the information about the workshops. But before that, I'd like to ask you to copy this, scan this QR code and do a quick poll. So now we have 5 minutes for you to do the poll. And for those of you who don't care at all about workshops, and if you're busy, you can feel free to leave. Now we're gonna just talk about the workshops from now on.
Su laiku sunkiai man, bet aš norėjau papasakoti, ar workshopų informacija yra prieinama ir online.
Bus dėsiu Facebook'e, pasistengsiu įkelti poną, taip pat bus Facebook'e ir jeigu nepamiršiu dėsiu reikalus. Jeigu turi Facebook'ą,
Super, labai gerai, nes aš iš tikrųjų turiu bėgti labai įdomu.
No problem.
Ačiū labai už įdomią paskaitą.
Jo, visi šitokie susitikimai bus nemokami, workshopai irgi bus nemokami. Pas mus mano tikslas, kad susitikimai su tuo preiksis. Kaip dažnai kas mėnesį vyksta tokie workshopai, konsultacijos. We are ready to start the next part, so please take your seats.
Tai va, baigsis mūsų kursas po
I can't wait to see the results, but I guess I have to do that after the rest of the presentation. So in this part, we're going to talk about the workshops. And I really expect that a lot of you are here because of the workshops, and I feel that like somebody has to tell you all about the actual vision of Vilnius School of AI. And my vision is to make this thing your gateway into artificial intelligence. I want you to provide like world-class artificial intelligence training, and to do that for free. I mean, I want you to like get the best knowledge, learn as fast as possible, and have fun while doing that. So that's my ultimate vision. And to achieve this vision, I have I basically do two things. I do these meetups and I do workshops. So meetups, pretty straightforward, you're in one of them, so that's how we go. Now let's talk about workshops. First of all, workshops, they're already in progress. We have 8 squads which are already in progress of actually learning artificial intelligence. I see a lot of people sitting, especially in the front rows. I know them. I know them because they participate in the workshops every Saturday. And for the rest of you, I'm going to tell you exactly what they are. So first of all, what are workshops? We will make you artificial intelligence expert. That's what workshops does. That's what workshops do. Makes you artificial intelligence expert. In the best case, even very, very good one. So how we are doing that? So I want you to teach real world practical artificial intelligence skills. I really hate a lot of what's currently being taught on artificial intelligence because it's so heavy on math, it's so heavy on the deep theoretical understanding of how computers work, how all these functions work, how linear algebra works, and don't get me wrong, these things are important, but they're not necessary. The same way, if you drive a car, you don't have to really well understand how the engine works, right? Just press the right pedal, go faster. Press the left pedal, it's kind of slowing down now. You steer with this round thing. That's how you're driving. I mean, it's totally different skills. Understanding the engineering of the car is very different from being a good driver. I guess world-class drivers, like Formula 1 drivers, yeah, we kind of have to know everything, but if you want to be just a practitioner, believe me, you don't have to know that much math. I mean, honestly, I was learning math probably 5 times in my studies in artificial intelligence. Do you think I learned it? I learned it 5 times and I forgot it every single time because I don't use it. It's not really that useful 99% of the time. So I want to really focus on the practical aspect. Time now. So time every Saturday. That means workshops take place every Saturday. In Saulėtekio Alėja, room 715. Thanks Code Academy for giving us this room, and that's where the workshops take place. We form squads of 14 people, and the idea of the squad is that you all learn together. I'll try to have as uniform squads as possible. That means people with similar interests, similar goals, similar level of computer knowledge and stuff like that, and I group you all together, and you all have this one goal to reach a certain checkpoint in your artificial intelligence learning journey. Okay, so I guess this all sounds very abstract, so I'll get to the more concrete parts. So we have 5 levels 5 classes, as I call them. So D class is the easy, it's for people basically who have zero knowledge of programming. Okay, and before we get like into like this gray area, I want to make sure that we are teaching you to program. We are teaching you to program artificial intelligence. We are not talking in theory about like different algorithms or whatever. Like in the end, you should be able to do at least proof of concept of some of your ideas. Okay, that's the goal. You don't have to be the top coder, but you also don't get to be a manager who just like understands in theory how the things are supposed to work. So you have practical application as well as like understanding how this can be used in the best way to solve some kind of problem. So like you can very quickly put yourself into one of these classes. And how many of you do you think, like for those of you who are not part of the workshops right now, how many of you do you think you belong to the D class? I mean, those who don't know anything about coding or who are not like, who don't work as programmers. That's my definition, right? C class is for people who know how to code. I mean, you can have like 20 years of experience, but those of you who don't know Python, okay? So you are programmers who don't know Python. Very good. B class is for people who know Python, but we want to learn data science. I mean, you might have some data science, like some NumPy knowledge, but you are not data scientists. Very good. A class is for those of you who are basically doing data science, machine learning, deep learning, any of those kinds of things. So A class is for you. It really goes deeper and into the best practices of deep learning. So, who are here? Okay, not a lot, but a few. That's very good. And finally, S class is for those of you who are very good at deep learning, and basically what you're looking for is some kind of like community or your group of people with whom you can create those projects.
So it's only regarding deep learning, no other types?
Like in like how it works right now, it's just deep learning. But maybe you can like give me an argument why it shouldn't be like that.
It's fine.
Oh, okay. I thought maybe you would like to say like, oh, but look, like machine learning with like these random forests, I can really kick your ass with your deep learning. Okay, yeah, so good. So that's S class. Let's talk about like one by one. So the goal of the D class is to learn code with Python. You're learning two things at the same time. You're learning how to code and you're learning Python. The only prerequisite is your motivation. We have a lot of, like we started with so many people who don't know how to code. Like we had 3D classes. We still have 3D classes, but we lost like 50% of the people because they lacked this necessary prerequisite, it's motivation. I mean, I give you the best resources which are on the internet, and I give you full support of your squad, I give you full support from myself, and what you have to do is really take this material and learn it. That's it. So your only thing, like your only requirement is motivation. It takes 12 weeks. I upped that a little bit. Initially it was 10 weeks, but I'm seeing that it's pretty much impossible to do the full D class program in 12 weeks. So it's like 12 weeks now, and after finishing that, you progress straight to B class. Okay, you skip C class because you learn all the same things. So now for those of you who know how to code, it's C class, and what you don't have to learn how to code because you know that, you only are learning Python. And you have to have like pretty decent programming skills. So you have to like have like what I'm saying is like at least 6 months of like professional programming experience. Okay, so that's how you know you should be in like C class or D class. If you have like 4 months, D class. If you have over 6 months, then you go to C class. It takes half as much time, only 6 weeks, and you also progress to D class. Then B class, you learn data science, and it's some like data science plus machine learning. That's the program of the B class. You have to know Python because we are doing everything in Python, and ultimately you progress to A class. In A class, you are learning deep learning, and I think I'm gonna expand this like a little bit. Currently it's 17 weeks, but I feel like I have so many good resources which are still supposed to be like in A class before you're ready to work full-time. Like not work full-time in S class, but before you really can be considered S class, you still have to learn a lot. So maybe this will change. I mean, it's the best time is right now to join A class because it's shorter now. And finally, S class. It's working on artificial intelligence projects, maybe winning Kaggle competitions, maybe like founding a startup. I know people who have done all of these things. I know one person who has done all of these things, like winning a Kaggle competition and founding a startup and getting financing and like kicking ass now. So you can be like one of those people. So, I mean, you are applying your deep learning skills and you're working on projects. And it takes like forever. I mean, it never ends. There's nowhere further to progress. So it's like infinite weeks. Finally, I guess a lot of you want to know how to do that. And by the way, before I kind of tell you about it, how many of you got today's email, like yesterday's email? I sent every one of you an email yesterday. How many have got that?
Via meetup.com?
No, just as regular email.
But it arrived in spam.
Yes, it arrived in spam, and I was so angry. Like I'm like seeing this tracking results on Mailchimp, and I see like 80% of Yahoo open that, 80% or like 90% of like other clients open that. Gmail, like 0.4%. And I was like, what? So Gmail for some reason blocked all my emails. And I was so angry because of that. And so I really hate email. Like I want to tell that right now before we get into discussions. So I hate email, so I'm using Slack. All the communication will be done on 2 channels, on Slack and on Facebook. If you are interested in workshops, then Slack is your channel, okay? You must register to our Slack. If you are interested in meetups mostly, so you don't have to register to Slack, Facebook is enough, or like meetup.com is enough, okay? So just getting that out of the way. I'll tell you how to like register to Slack. So I had like an auto posting on Facebook. So there should be a new post on our group with a link to our Slack channel. So you can check it out right now and register to our Slack. All the information about the upcoming workshop groups, like squads, it's gonna be posted on the general channel. Okay, so there's nothing there right now, but I'm gonna post that at latest at the end of the week. I'm still working out a lot of things. I still have like pretty much my whole schedule right now booked with the other 8 squads, but I'm working things out how to make it happen for the new guys. Okay, so at the end of this week or earlier, we have some so at the end of this week or earlier, we'll have you'll have full information, what to do, then to do what form to fill to be able to do workshops, right? And so all the information will be on the general Slack. You'll get a registration form, And this registration form basically asks you like a lot of questions and determines in which squad you will be placed. It depends on your availability, your motivations, how many hours per week you can spend, what's your current like Python level, what's your current like programming level, and so on and so on. So with that being said, do you have any questions about the workshops? No questions.
What is the first one?
Yeah, so I cannot tell you exactly right now. As I said, I'm still working things out, but optimistically, in 4 weeks. Like, not this Saturday, not next Saturday, not next Saturday, but then next Saturday. Yes?
Do you have like some exams or like test of knowledge if you want to progress from like one to another level or something like that, or you just
you have to do a project. Like all the classes finish with projects, and you have to do a project. If the project is good enough, you'll progress to the next class.
How long lessons last during Saturdays?
So, like, to make sure what's going to happen on Saturdays, we are not going to do lessons. Like, I don't want to go into a lot of details. Basically, you will get your plan, what you have to learn for the next week. Because we have like 1 hour, okay? In this 1 hour, what we're gonna do is, like what we are doing right now, is we check on everybody how we are doing. Then we get like how to fix things. Should we like make them faster, like learn more, or learn less, so everybody can like work at the same pace. And finally, I'll give you the goal, what to do for the next week. Yeah.
And do you necessarily need to engage with one group, or
Yes,
do you have your personal base?
You have to work with one squad. This one squad is your like, they are responsible for you passing your like class, okay? And you are responsible for their like knowledge. I mean, so this is like kind of a reinforcement network. If everybody helps everybody else, then you have a very, very, very strong community. So that's what squad is. It's pretty small, so you can know everybody, you can meet up with them. A lot of the squads like meet every week, and they discuss their learning, the problems they have, like how other people solve them. So that's like a very small community of friends who are learning exactly the same thing as you. Yes?
So what's the time investment each week?
It really depends on like your goals. It can be as little as 5 hours per week, but I like initially all the courses are designed for 10 hours per week. If you can do that, you'll be like doing enough. If you can do 5 hours, you can still go, but you'll have to like really work hard on those 5 hours, and you'll maybe not learn as much. Yeah.
I actually couldn't hear the very first question, but was it about when the next rules are starting? Is that in 4 weeks? So.
Yes.
Okay.
It's when the next one is. And you had a question?
I have a question. For each of those courses, is there like a program of topics the course will cover? For example, the Python course.
Mm-hmm.
Because if you're already a programmer, then 6 weeks for Python sounds quite a lot. It's something you might be able to cover much faster at your own pace if you do topics in advance. Maybe even skip the class.
So first of all, you won't, because we have like a lot of I have like 3 C classes, and like they vary in their skills like a lot, and nobody can do it. Like, okay, 1 C class is doing that in 5 weeks, okay, but still you have to do a project. That's 1 week, so you have like basically 4 weeks to do these things, and they want to really make sure that we don't come back to this.
I mean, if you can pick up, you expect that at the end of the class the person will have a certain level of knowledge, right?
Yes.
What I meant to say is that maybe it's possible for the person to reach that level of knowledge on his own if he knew the prerequisites without taking the class, if he's already a professional programmer.
Sure, I guess that's doable, but still, I would recommend going through the C class still. I mean, it really depends on you. If you manage to like learn Python really well in those 4 weeks, which I'm sorry, but I doubt you, but you can prove me wrong, then by all means register to be class. But you better make sure. Yeah, I can like ask me on Slack. I'll send you the list of topics. Sure.
So you said there's some projects. Are they collaborative or individual projects?
It's up to each person. It can be either way. It can be like up to 3 people. So 1, 2, or 3. So last few questions.
How much does it cost? Is it for free?
Yeah, so he's asking how much does it cost? It is for free. You don't like, what you might have to do is pay for some Coursera courses, because very recently they made the materials inaccessible and you actually have to buy it. So that's the only thing.
Actually now Coursera has offer until the end of the month you can take 7 days any courses for free, I think, something like that.
Yeah, they have a free trial for 7 days, but that's not nearly enough. I mean, you are spending like the shortest course is 6 weeks, so no way to do that. And that's actually not for C class, that's for A class.
Is there any other conditions should know, or
Can you give me an example?
I don't know.
Yeah, there are some other conditions. You must be able to meet on Saturdays. Otherwise, there's a different squad, like an X squad. X squads are for people who, like, for some reason cannot meet on Saturdays. So they are doing this thing like most of them are doing this thing like individually. Or if you find like at least 4 people, you can do that as a remote squad. So you all work remotely, but you are still a squad. Or you can do that like, I mean, there's also a way to study all the material individually and never meet up with me.
Is there a fixed time for the meetings? Sorry.
Is there a fixed time
Yeah.
for meetings? Yes, absolutely. Everybody has their fixed hour, and so right now I'm working from 9 till 5. On Saturday, all the hours are filled, so I'm like thinking how to make room for the new guys. And you had a question?
The same question.
Okay, see, you can be in one squad. Yeah, so thank you all for coming. I'm still gonna hang out here for like 10 or 15 minutes. Feel free to talk to the people right here, because we are all interested in artificial intelligence. Make some connections, make this meetup count, or just go here, talk to me. Thank you all for coming. You're very good.